In this third devlog, we're going to look at how we handled complex input requirements inside the first Unity Open project. Open projects are small, open source games where the creator community is free to collaborate and contribute actively to the game development journey in any of its aspects. The first open project is an action adventure titled Chop Chop. You can find the link to the GitHub project and all the other relevant links to learn more and get involved in the video description below. We are making the game using Unity 2019.4 LTS, which will guarantee us the best stability during development. But since we wanted to make the contents of this devlog series available to you in the latest Unity version, we upgraded the project to work on Unity 2021.1. You can find this 2021.1 version of the project on a Git branch on the original repository called devlogs/3-input. Chop Chop is a single-player game where you control a character from a third-person perspective. We started with the intention of supporting gamepads first, but since not everyone has a gamepad readily available, we also added support for mouse and keyboard. You can move, look around, jump, and many more things like interact, fight, initiate a dialogue, pause the game, and navigate through different menus. All these actions are bound to different physical inputs that can change depending on the device used. So naturally, we decided to utilize the input system package. Thanks to an input action asset, which you can find inside the folder Settings, Input, it is possible to bind actions defined by a name to different kinds of physical inputs, potentially 2 or more per action. For example, we associated the jump action both to the space button on the keyboard and to a button on the gamepad. This abstracts the input logic, allowing us to listen for these actions without caring about which device is used to produce them, which also improves scalability and multi-device support. For instance, it would be very easy to port this game to consoles by just adding the right additional action bindings. As a second tier in this system, actions are then grouped in an action map which defines a set of controls linked by a common purpose. At the moment, we have one for gameplay, one for menus, and one for dialogues. Once the input action asset is set up, there are multiple ways to access its data. The simplest approach would be to use the component-based workflow, which we recommend to get started quickly, and is useful when prototyping. However, we decided to go with another slightly more elaborate way to get more control. We asked Unity to automatically generate a C# wrapper class for the input actions, which in turn exposes a bunch of interfaces to implement in scripts. This removes the need to manually look up actions and action maps using their names by string, and also provides an easier way to set up callbacks. Now, instead of referencing the C# wrapper in any script that needs to respond to input, we decided to build a layer in between this input detection C# wrapper and the end scripts which need to access that input. There are a couple of reasons why we built this intermediate layer, and we'll go over them in a second. Initially, this layer has been conceived as a mono-behavior script, but thanks to a suggestion from a community member, it later became a scriptable object. This means that now we can access the input layer from any script, due to the fact that scriptable objects are assets and thus scene independent. By the way, if you're curious about how we've implemented and designed our game architecture around scriptable objects, check out the previous devlog linked below. You can find this scriptable object named Input Reader under Scriptable Objects, Input. Now let's dive into the Input Reader class. Inside this class, we listen to all the actions of the action maps and, for each one, we raise a Unity action. The scripts that need inputs can now subscribe to these Unity actions and respond accordingly. For example, each time the keyboard or gamepad buttons related to the attack action are pressed, the onAttack method is called. The method receives a callback context data structure that contains information about the input being processed, like its phase and its value, if applicable. Actions will go through several possible phases, and each one of them can be useful for a certain scenario. For instance, the performed phase doesn't happen when an input begins, but when it is confirmed, since it's possible to set up an action so that the input is considered valid only when the button is pressed for a minimum amount of time. In this case, we invoke the attack event when the attack input is performed. A good example where we take advantage of the phase property is in the onJump function. Here, we distinguish two cases. When the input becomes performed, we raise the jump event, and on button release, we raise the jump canceled event. This allows the character script to process one button as two separate events, which in turn allows us to better control the arc of the jump. We apply an upwards push as soon as the input enters the performed phase, and we stop doing that when it becomes canceled or after 0.4 seconds, allowing gravity to bring the character back down. We implemented a more complex scenario to control the camera movement. The requirement is that to rotate the camera, the player can use either the mouse or the gamepad's right stick. But we want to rotate the camera only if the right mouse button is pressed. In our Camera Manager script, we subscribe to the Camera Move event, and inside this function, we perform some checks on the input before rotating the camera. In particular, in the handler that receives the event for the mouse movement, we check that the right mouse button is currently pressed before we actually move the camera. As for the camera speed, since mouse delta and joystick provide values of wildly different scale, we adjust the scale using processors directly within the Input Actions interface. So in the code, we get a clean vector 2 of similar scale regardless of the device used. As we mentioned before, all the possible actions that the player can perform are grouped into action maps. An action map is a set of controls dedicated to a particular moment in the game. There are times in the game where you might need to change the way an input behaves and differentiate between normal gameplay, a dialogue phase, menus or cutscenes, and more. For instance, inside a menu, to confirm a selection, you use a specific button. This button may be the same physical input that you use to perform a jump or an attack during the gameplay phase. For that reason, the input system allows creating multiple action maps and switching between them at runtime, enabling and disabling entire groups of actions at once. Since our input reader layer is a scriptable object, we're able to switch between action maps at any point, calling the dedicated methods on it. Also, some of the actions in the mapping retain the same name across action maps to keep consistency. For example, the move selection action exists in both menus and dialogue action maps. This allows us to use a single method in the input reader to react to both actions, since even though they belong to different action maps, they are supposed to behave in the same way in these two game scenarios. To use the input system to navigate menus and interact with the UI, we used a combination of built-in components and a couple of custom components we designed for our specific needs. As a start, the generic Event System component works in conjunction with the one called Input System UI Input Module, coming from the Input System package. These two take care of broadcasting navigation events. With this simple setup, we can already move our selection and activate buttons. However, we also wanted to allow navigation of the UI with either mouse or, as an alternative, one between gamepad or keyboard. This involves some extra code because while the keyboard and joypad move the highlight to adjacent controls, the mouse cursor can jump to any button it enters, and that's what the script Mouse Selection Handler takes care of. In addition to this, we wanted the highlight to disappear when the mouse begins to move to simulate a fully mouse-driven UI. For instance, when we move across the menu with the mouse, the system detects which elements the mouse is currently hovering on, and if a click occurs, the selection should be activated. If we move again using either the keyboard or the gamepad, we should resume the navigation from the last element selected by the mouse. You can explore this simple implementation of a hybrid UI in the scripts called Menu Selection Handler and Multi-Input Button, both located in the folder Scripts, Menu. Inside them, you'll easily see how we inject our custom behavior in the regular flow of events in the Unity UI. As with many parts of this project, this is just the beginning implementation. Now let's see what our next goals are with the input in the game. One of the things we want to add is the possibility of rebinding actions. Covering this is very important for accessibility, to let each user choose the controls that fit them best and to accommodate the usage of custom-made controllers. The runtime rebinding feature was shown in a recent video about the input system. So if you want to know more, you can find the link in the description below. Also, with regards to binding of inputs, we need to make sure to properly communicate and show them to the player during gameplay and in menus. For this, another important thing to implement is a UI to show input mapping in the menus for both schemes, gamepad and mouse and keyboard. Keep yourself updated on the first open project by following the roadmap, the daily changes in the GitHub repository, and the bi-weekly live streams. The project will keep improving and changing during development on the main branch, but remember that you can always find this 2020.2 version in a branch on the repository called devlogs/3-input. We can't wait to see your feedback and contributions. Thanks for watching.